Welcome to our Quantum Deep Dive. Today, we're digging into the story of a true pioneer, a physicist whose really radical idea back in the late 90s pretty much laid out the architectural DNA for an entire field of quantum research. We're talking about Bruce Kane, the guy who envisioned the silicon-based quantum computer.
Right, and our guide for this whole deep dive is a fantastic, super detailed essay on Kane's work written by Jörg Owe Schneppet. His analysis is what we'll be unpacking today as we get into this incredible story.
Okay, so let's set the scene here. The 1990s. What a time for quantum theory, right? You've got these incredible, mind-bending algorithms that promise to do things like crack modern encryption, revolutionize science. The theory was solid, but the actual machine to run it on? Yeah, that was a complete mystery. It was seriously one of the biggest challenges in all of experimental physics.
So how did Kane approach this whole mess? Well, we're going to start with the hardware problem that everyone was facing, and then dive into his absolutely brilliant silicon-based solution. We'll break down his qubit design piece by piece, see how his vision just ignited a global research effort, and then trace its legacy right into the quantum chips of today. And we'll wrap it all up with his ultimate vision: one atom, one qubit.
So yeah, let's start there, with that massive gap between the promise of quantum computing and the physical reality of the 90s. I mean, it was more like a chasm between what the mathematicians proved was possible and what engineers could actually, build. And you can just feel the pressure building on this timeline. I mean, 1994, Peter Shor drops his algorithm, and it proves a quantum computer could basically break the backbone of modern internet security. Suddenly, the entire world of cryptography has this theoretical expiration date looming over it. Then, just 2 years later, Lovegrover shows how quantum computers could search databases exponentially faster. So the software was basically ready to go, but the hardware? Totally missing. And this kicked off a mad dash, a global scramble to build the fundamental piece of it all, a stable, controllable, and scalable qubit.
And building one was, well, it was a monumental task. This is the checklist, the wish list, that any potential qubit had to satisfy. It was later formalized as the DiVincenzo criteria. You needed a quantum particle you could reliably set to zero. Then you had to protect it from the noisy outside world for as long as possible. That's coherence, so it doesn't just forget what it's doing. And then you had to precisely control it to perform calculations. That means shielding it from, everything. Stray magnetic fields, thermal vibrations, you name it. And after all that, you had to be able to actually measure the result. Oh, and by the way, you needed a way to do this not just for one qubit, but for millions. It was a physicist's nightmare.
And this is exactly where Bruce Kane walks into the story. So you have all these research groups around the world exploring really exotic materials, trapping single atoms with lasers in giant vacuum chambers, or building these incredibly delicate superconducting circuits that had to be cooled to near absolute zero. But Kane, a physicist with this deeply pragmatic streak, he just asked a totally different question. And that question itself was the real innovation. It was so simple but so profound. Instead of trying to invent some brand new technology from scratch, Kane's idea was basically to hijack the most advanced, most mature manufacturing ecosystem on the planet, the multi-trillion-dollar semiconductor industry. Why go through all the trouble of building a quantum computer in a pristine lab vacuum when you could potentially just print one on a silicon wafer, just like the chips in our phones and computers?
Now, this idea didn't just pop out of nowhere. Kane's time down in Australia at the University of New South Wales was absolutely crucial. He was completely immersed in an environment that was at the cutting edge of semiconductor physics and nanofabrication. He saw firsthand the incredible precision that was already possible with silicon, and it was right there, at the intersection of quantum theory and practical nanotechnology, that his vision for a silicon quantum computer was really born.
Okay, so let's pop the hood and get into the technical details. How did Kane actually propose to build a qubit using silicon? This is the blueprint he laid out in his absolutely groundbreaking 1998 paper in the journal Nature.
All right, here's how the blueprint works. Step 1, the foundation. You start with a crystal of silicon-28. Now, this specific isotope is so important because its nucleus has zero spin, which makes it a perfectly quiet, non-magnetic background for the very delicate qubit. Step 2, the qubit itself. A single phosphorus atom placed with incredible precision inside that silicon lattice. Step 3, the information vault. This is where the quantum information is actually stored, and Kane proposed using the nuclear spin of that phosphorus atom. Why? Because nuclear spins are incredibly stable. They're super well isolated from all that environmental noise. But that stability also makes them really hard to control. Which brings us to step 4, the control key, the phosphorus atom's extra electron. Its spin is way more sensitive and can be manipulated by external fields. So the big question is, how does the key actually turn the vault? The link is this fundamental piece of physics called the hyperfine interaction. You can think of it as a natural magnetic handshake between the electron's spin and the nucleus's spin. Kane's genius was realizing that you could use electric fields from tiny little electrodes on the chip's surface to gently tug on the electron, and that in turn would modify the strength of this interaction. This basically gave him a dial to control the supposedly inaccessible nuclear spin, and all with simple electrical signals.
And this is how he designed the whole control system. He imagined these two types of tiny electrodes, or gates, layered right on top of the silicon. You have A gates, which are placed directly over a phosphorus atom. They apply the electric field to control that individual qubit by tuning its hyperfine interaction. And then you have J gates, which are placed between two qubits. They would control the interaction between their electrons. This would let them make the qubits talk to each other, which is how you create the two-qubit logic gates that are essential for any real computation. It was a complete, all-electrical architecture, just like a classical chip.
So this 6-page paper, it was way more than just a proposal. It was a catalyst. I mean, it landed like a thunderclap in the research community. It set off this incredible chain reaction that really defined a whole new direction for quantum computing research for decades to come.
And almost immediately, research groups all over the world just took Kane's blueprint and ran with it. Back at his old stomping grounds, UNSW in Sydney, Michelle Simmons' group took on the huge challenge of actually placing single phosphorus atoms with atomic precision. Over in the Netherlands, TU Delft adapted his spin-based ideas for quantum dots, these tiny semiconductor crystals that could trap electrons. And it wasn't just in academia. Tech giants like Intel saw the potential and launched their own massive research programs. Kane had officially started a global race.
You know, the term that really made investors and engineers sit up and pay attention was CMOS compatibility. This was Kane's ace in the hole, his trump card. CMOS is the standard battle-tested process that's used to make every single computer chip in your phone, your laptop, literally everything. The promise was that one day you could manufacture quantum processors in the same factories as classical ones. You could leverage decades of optimization and trillions of dollars of investment. This idea connected the exotic physics of a single atom to the very real, very powerful engine of industrial mass production. It was a path to scalability that no other approach could really offer at the time.
Okay, so let's fast forward to today. After more than 2 decades of really intense research, all inspired by that one 1998 paper, where does Kane's vision stand now? How does the silicon approach actually stack up against its main competitors?
All right, let's break this down. On one hand, you have superconducting qubits, the kind used by Google and IBM. They are known for incredibly fast gate speeds, but they really struggle with coherence. They basically forget their quantum state really quickly. We're talking microseconds. Trapped ions are kind of the opposite. They have amazing fidelity and coherence, but their operations are comparatively slow. And this is what really highlights the sweet spot Kane was aiming for. Silicon spin qubits offer this powerful combination, potentially massive scalability because of CMOS manufacturing, and incredibly long coherence times, all thanks to that quiet silicon environment. The trade-off? The huge challenge of fabrication precision.
And that challenge is definitely not a trivial one. To make Kane's vision a reality, you need to place and wire up individual atoms on a scale below 10 nanometers. I mean, that is at, or even beyond, the absolute limits of current manufacturing technology. And what's more, when you pack qubits that closely together, you have to worry about something called crosstalk, where one qubit's operation accidentally influences its neighbor. These are the big engineering hurdles that research teams are still working tirelessly to overcome.
So as we start to wrap this up, what is the ultimate legacy of Bruce Kane? The thing is, it's so much more than just a single design for a qubit. It's really a fundamental shift in how we even think about building quantum machines.
This quote from the original essay by Jörg Oa Schneppet just captures it perfectly. Kane didn't hand the world a finished quantum computer on a silver platter. What he did was arguably much more important. He provided the architectural blueprint, and he asked the right question at the right time. He opened a door and showed an entire generation of scientists a viable path forward, a way to merge the quantum world with the silicon world.
And the proof that this path works is right there in the numbers. Researchers who followed Kane's direction have demonstrated coherence times for a nuclear spin qubit in silicon exceeding 30 seconds. In the quantum world, where operations happen in nanoseconds, 30 seconds is an absolute eternity. It's just a direct, stunning validation of his core idea, that his single atomic nucleus, nestled in a quiet silicon crystal, is one of the most stable places in the entire universe to store a bit of quantum information.
And that leaves us with the big question for the future, doesn't it? The race is still on. Superconducting and trapped ion systems, they definitely had a head start. But as we move toward fault-tolerant quantum computers that are going to require millions of high-quality qubits, will the quiet, the dense, and the potentially mass-producible silicon qubit, the one born from Bruce Kane's vision 25 years ago, ultimately win the day?
And that's all the time we have for this explainer. We really hope this look into Bruce Kane's work gave you a new appreciation for the kind of visionaries who really do build the future. A huge thanks again to author Jörg O. Schneppat, whose work was the foundation for our analysis today. For more of his insights, you can visit schneppat.de. Thanks so much for watching.
Schneppat.de is a private project by Jörg O. Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.